Hi, I am Zhu Xiaotang. Today I will talk about Eulerian orientations and Hadamard codes, a novel connection via counting. This is a joint work with Shuai Shao, when I was an undergraduate student at the University of Science and Technology of China. Currently, I am a first-year PhD student at University of Wisconsin-Madison. This is an outline of this talk. Let's begin with Eulerian orientation problems. The history of Eulerian orientation problems goes back to the famous seven bridges of Königsberg problem, which is posted by Euler. This problem asks if there is a cycle that visits every edge exactly once for a graph, and this cycle is called an Eulerian cycle. And we know in the example of seven bridges of Königsberg problem, there is no Eulerian cycle. Similarly, we can define an Eulerian orientation of a graph. It's an assignment of directions to edges of the graph, such that at every vertex, the number of outgoing edges is equal to the number of incoming edges. This graph is an example of Eulerian orientation. Euler proved that a graph exists an Eulerian cycle is equivalent with a graph exists an Eulerian orientation, and it is equivalent with every vertex have even degree in that graph. In terms of complexity theory, the decision problem of the existence of an Eulerian orientation of a graph is in P, because we only need to check if for every vertex it has even degree. We also care about the counting version. We want to compute the total number of Eulerian orientations of a graph. In 1996, Mihail and Winkler proved that counting the number of Eulerian orientations of an undirected graph is sharply complete. However, what if we consider the problem of counting Eulerian orientations in a graph with the direction of some edges are fixed? Here is an example. In this four regular graph, exactly one edge at every vertex are fixed to be outgoing edge. And counting the number of Eulerian orientations for a four regular graph comes from the famous six-vertex model in statistical physics. And this problem is well studied by Cai, Fu, and Xia in 2018. They showed that counting the number of Eulerian orientations in a four regular graph with one outgoing edge fixed at every vertex is polynomial time computable. More generally, we can define counting restricted Eulerian orientation problems. The problem is parameterized by f, which is a set of Boolean constraint functions. And a constraint function is also called a signature. A signature f is an LTN function, which takes Boolean input of length n and maps to complex numbers. But in this paper, we mainly care about the output is 0 or 1. We also require f is EO. That means every signature in f must have even degree and take non-zero value or take value 1 only if the input contains half zeros and half ones. This corresponds to the requirement that in an Eulerian orientation, the number of incoming edges is equal to the number of outgoing edges at every vertex. More formally, the problem counting EOF has an input graph G, while every vertex is labeled by some constraint function FV. And we consider all possible assignments of directions to all edges. And we assign 1 to the outgoing endpoint of that edge and assign 0 to the incoming endpoint of that edge. So, every vertex will have degree V inputs. Each of them can take 0 or 1, corresponding to the edge incident to the vertex is incoming or outgoing. And such an assignment is valid if and only if it satisfies the constraint at every vertex. And we want to count the number of all possible valid assignments sigma. So the output is in the form of sum of product. The summation is over all possible direction assignments of edges, and such an assignment is valid if it satisfies all the constraints at f. So we have a product of all the constraint functions at v. Here are some examples. First, if I allow f to take value 1 at every input that contains half zeros and half ones, then this problem exactly counts the total number of Eulerian orientations of the input graph, which is sharply hard. Another example is computing partition function of 6-vertex model, which is mentioned previously. Here, the constraint function set consists of one single function, which takes value 1 on 3 inputs. They are 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1. And because the first bit is always 1, that corresponds to one edge is fixed to be 1. And because the constraint function should be EO, so for the last 3 bits, there are 2 zeros and 1, 1. So this problem, parameterized by this F2, computes the number of Eulerian orientations for regular graph. Or we can say it computes the partition function of a 6-vertex model, and this problem is tractable. Why we study counting EO problems? First, because it's a very expressive framework. Many problems can be expressed as a counting EO problem. For example, the original version of counting unrestricted Eulerian orientations. Also, in 2020, Cai, Fu, and Shao proved the theorem that shows counting constraint satisfaction problems can be expressed by counting EO problems. And we know that counting CSP is very expressive. And this theorem shows that counting EO problems is even more expressive than counting CSP. And the evaluation of the Tott polynomial at the point 33 can be also expressed in the EO framework. Other examples including calculating the partition function of 6-vertex model. Another reason to study EO problem is that it may play a crucial role in a broader picture. It may serve as a building block for the classification of Holland problems, and Holland problems is a more expressive counting framework. And there are many achievements for the classification of Holland problems. One of them is the classification for all real-valued Holland problem, and this is based on the complexity classification for counting EO problems with an additional requirements for the constraint function, and that's called arrow-symmetric property from physics. And if we want to prove a complexity classification for all complex Holland problems, we should first prove a complexity classification for counting EO without assuming the arrow-symmetric property. And in this paper, we considered the 0-1 valued counting EO problems without assuming the ARS property, which may serve as a building block for the ultimate classification of all complex valued Holland problems. Now let's take a little detour to the Hadamard codes. First, the Hadamard matrix Hn is a square matrix of size n, such that all the entries are 1 or minus 1, and Hn times Hn transpose is equal to n times identity. Sylvester gives a construction of Hadamard matrices of size of power of 2, and it is constructed recursively. By the definition of Hadamard code, or by the construction of Sylvester, we know that the first row of the Hadamard code will be all ones. the Hadamard code corresponds to those code words which we view every row of the Hadamard code of the Hadamard matrix a code word, and we map 1 to 1 and -1 to 0. Then it becomes a Hadamard code. And by the Sylvester's construction, we know that the first row of the Hadamard matrix is all ones, and we remove it. It will become a balanced Hadamard code. Balanced means that for every code word, it contains half ones and half zeros. And I will list our main results. First, we introduce new tractable classes D1 and D0. They are defined inductively for counting U problems, and they are a generalization of the tractable class for the 6-vertex model. And problems parameterized by this tractable class can be solved by a chain reaction algorithm. We also give a characterization of the first level hierarchy in the tractable classes, and it turns out that these tractable classes can be characterized perfectly by the balanced Hadamard code. Finally, we prove the no-mixing theorem for D1 and D0. Although D0 or D1 alone is tractable, if we have them simultaneously, the problem will become hard. And the proof of the no-mixing theorem uses the characterization theorem. To clarify the chain reaction theorem, let's revisit the 6-vertex model. In this 6-vertex model, every vertex is labeled a constraint function that takes the value 1 at inputs 1, 0, 1, 0, 1, 0, 0, 0, or 1, 0, 0, 1. If we write the constraint, the non-zero input in a row, then we will get a matrix. If we view every non-zero input as a code word, then it is exactly the balanced Hadamard code of size 4. Then we may think about what happens if every vertex of the graph is labeled by a signature corresponding to a balanced Hadamard code. For example, this is a 3-dimensional grid of 8 regular graphs. And at every vertex, it is labeled a signature corresponding to a Hadamard code of size 8. And this problem turns out to be also tractable. More generally, if we let the F to be the signatures given by the balanced Hadamard code, then the U problem parameterized by F can be solved by the following chain reaction algorithm. This is an informal description of the chain reaction algorithm. First, we start at an arbitrary vertex U, and it turns out to be there will be an outgoing edge at U, and we follow this outgoing edge and we move to V. And the variable of Fv corresponding to the incoming edge is pinned to be 0, because we assign 0 to the incoming endpoint of that edge. Then after pinning 0, this Fv will become a phi. This is a property of the Hadamard code. And then there will be another outgoing edge at V. And we follow that outgoing edge at V and can repeat the process above. And after all outgoing edges are used up, then finally we will get a signature grid, where every signature at every vertex is an affine constraint. Then we can solve the problem by Gaussian elimination. Here are more explanations for this algorithm. First, why there is, in the initial step, why there is an outgoing edge at U. That's because the constraint at U is given by an Hadamard code, and in the Hadamard code, one position is fixed to be 1. That corresponds to an outgoing edge at U. Second, why after pinning 0, Fv becomes a phi. The first case, if we pin 0 to a balanced 1 Hadamard code, it will become a phi. That's a property of the Hadamard code. And second, we may pin the vertex as a constraint function at f twice. That's equivalent with pinning 0 to an affine signature. And there is a pairwise opposite property of affine signatures guarantees that pinning a 0 to an EO affine signature, it will produce new delta 1 factors. So we can do the propagation. And in the analysis of chain reaction algorithm, we only uses the two properties of the Hadamard code. First is there is a column of the Hadamard code fixed to be 1, that corresponding to one outgoing edge. And second, after pinning 0, the Hadamard code becomes affine. So we extract these two properties to define the so-called delta 1 affine kernel signatures. The first property corresponds to there will be an outgoing edge fixed at every vertex. And the second property corresponds to that after pinning 0, the signature becomes affine. And the same analysis shows that the chain reaction algorithm applies to counting EOF, while F is the signature set consists of delta 1 affine kernels. And the balanced 1 Hadamard code satisfies these two properties, so it belongs to delta 1 affine kernels. We ask the following question: is the converse also true? That means, if F is a delta 1 affine kernel, can it be characterized by the balanced Hadamard code? And it turns out to be true. The main technical contribution of the paper is this theorem. An EO signature F is delta 1 affine kernel if and only if it is a balanced Hadamard code and up to a concatenation. Here is an example. This is a delta 1 affine kernel, and this is also a balanced 1 Hadamard code of size 8. Actually, the chain reaction algorithm works for general tractable classes defined by D1. And the D1 signatures also have the two properties. First, it can factor out a delta 1 factor. That corresponds to, at this vertex, there will be an edge fixed to be outgoing. And after pin 0, it will become affine. Either it will become affine, or again, I can extract a delta 1 factor and recursively do this propagation. So that's the D1 class is defined recursively. And the delta 1 affine kernels are subclasses of D1. Actually, they are the first level hierarchy in this recursive definition. Symmetrically, we can also define D0 signatures by switching 0 and 1 everywhere in the definition of D1 signatures. Finally, we prove a no-mixing theorem between D0 and D1. Here is a proof sketch. First, we prove for the simplest D1 and D0 signatures F2 and G2. We prove that the EO problem characterized by F2 and G2 is sharply hard. And the signature F2 is exactly the constraint function for the 6-vertex model. And this is well studied, and we can prove this problem parameterized by F2 and G2 is sharply hard. And second, we prove there is a no mixing between the delta 1 affine kernels and delta 0 affine kernels by realizing F2 from any possible D1 affine kernels and realize G2 from any possible D0 kernels. And this will use the characterization theorem for delta 1 affine kernels and delta 0 affine kernels. Finally, we prove the general theorem by induction. Here are some future works. We want a complexity dichotomy for counting EOF. That means, given the signature set F, the problem parameterized by F is either Fp, which means it's polynomial time computable, or it's sharply hard. Our work does not lead to a complete complexity dichotomy for counting EOF. even we restrict signatures in F only take 0 or 1 values. Recently, Meng, Wang, and Xia find strictly more general tractable classes than ours. However, their work does not lead to a complexity dichotomy for counting EOF either. So, we guess there might exist more tractable classes for EOF. And that's the obstacle for establishing a complexity dichotomy for counting EOF. Thank you for listening.